Hello, today we are going to review the paper Google File System. It is a scalable distributed file system for large data intensive application. It was created by engineers in Google. To name them a few: Sanjay Himawat, Hord Kobiov, and Shun Tak Leong. We'll cover the essential part of Google File System. So let's start with why the GFS had to be born. So it was designed to meet Google's data processing needs and computing environments. So at that time, Google was scaling up big time because it was coming up as the biggest search engine, and distributed system concepts and sharding data was not a very new concept. But at the time this paper was presented in the conference, which was one of the most eminent conference, it was realized that the way Google was able to achieve handling data of such a large scale, it made sense. It actually was uh, a great innovation at that time. So at that time, Google had a huge data processing needs, like crawling the engine, processing a lot of logs, storing a lot of logs, and suddenly the engineers realized that the handling such a huge data with required redefining the file systems on top of which it was based. The data was stored, and they had to do certain things. So the reasons why they did was, first was all the distributed system they were building on top of hundred of thousands of storage machines, which are inexpensive hardware, and the software and the hardware they knew would go down due to various reasons like human errors, operating system bugs, and failures of disk memory, etc. So the file system had to be such that it could monitor, detect errors, and tolerate the faults, and be able to automatically recover from that. Secondly, the engineers realized that the amount of the size of the files that they were dealing was not normal, but multi GB files and TBs of files was a norm, and to have these such huge files on top of KB size files on a node was not going to solve the problem. So as a result, they had to redefine various IO operations and block sizes. Thirdly, a lot of this data set was majorly about uh, appending the data rather than doing a random access, right? So, so few of the data were like large repositories where the programs would run and scan those data sets. Few of them were like data streams which are generated by a lot of running applications, and few of the data sets were archived data. Few of them, like in case of MapReduce, it was like you were putting intermediate results into one machine and taking out the output and putting that into another machine. So uh, given the access pattern, it was realized that the focus had to be on optimizing the appends and making sure these appends were atomic in nature. Caching the data on the client side and on the server side was not a big requirement at that time. The fourth was a lot of numerous applications were being built out at Google, and in fact, the engineers who were actually building the Google file system were from these teams which are building huge data processing pipelines or applications. So they did a lot of back and forth uh, in doing trade-offs and then compensating with that either in the application layer, and then further hardening or further bringing those features into the GFS, and then making sure that applications could deal with a few of the trade-offs they decided. So one of them was relaxed consistency, and it was done to simplify the design of Google file systems, rather than complicating it. The workloads primarily consisted of streaming rights, as I told. where an offset, start offset and end offset is given, and a huge amount of data was being read, like in kbs, hundred of kbs, or in mbs. There were need of running very small random reads as well of few kbs at some arbitrary offset, but uh, the focus was on optimizing for large streaming reads. Secondly, the teams uh, wanted to perform the batch processing at a high rate rather than focus on optimizing on latency of a single read or write. So uh, so so the bandwidth utilization was the major reason for coming up with any design rather than improving on point read latency. So the writes, again, I said, were majorly sequential. It sequential, or even if it was concurrent, it was majorly okay to have append based writes, is what it was realized. So based on these assumptions, Google team decided on few APIs. So create, delete, open, close were no brainer. But then there were APIs like read files, write files, just like Unix API provides, giving a file name, start offset, and an end offset. For the write, it would also give a data. But it also defined a couple of more operations like snapshot. So snapshot was like cloning the whole data set and creating a new copy of it. Secondly, the one of the major API that would be heavily used was record appends, because there you would give a file and data, but don't need to give an offset like you would give in any other system, because GFS would append the file at the offset of its own choice. And this was made atomic so that there could not be, even if there were concurrent appends, there would not be any interleaving between them. So files were also organized hierarchically, at least for the nomenclature, but ultimately in master, these were stored in a different format, which we'll go in a little bit later. So let's talk about the architecture of uh, the Google file system, and it starts with the basic unit of the system, that is a chunk. So what is a chunk? So as we know, as we can intuitively think, the files were actually divided into fixed size chunks. So each of the file, which would be multi GB, had to be given a unit of storage, and that was decided to be 64 MB. And these 64 MB file chunks would be given a handle, which would be a 64-bit chunk handle, and that was assigned by the master at the time of the chunk creation. And chunk server store these chunks as Linux files, and the read write data based on chunk handle and an offset. So these chunks were actually replicated on multiple machines, so that even one of the machine goes down, the other chunks are still available for reading or writing. So this was something that satisfies one of the assumption or the requirement, which is to have a fault tolerant system, even in midst of huge number of machine failures, etc., etc. We'll go deeper into this aspect, but let's say why the size of the chunk was decided to be 64 MB. It could have been lesser, it could have been 10 MB, or it could have been bigger, let's say 1 GB. So large chunk size reduced need to interact with the master. So what it means is that if if a client goes to the master, fetches, so we'll see the whole architecture design, but think about it like, uh, client doesn't need to know the chunk address again and again, and it doesn't need to poll for the address again and again, and it can cache that information with it and directly hit the data servers, which were the chunk servers, to for the chunks. So it reduced a lot of hop and time, and also helped scale the system. A persistent connection could be kept with these large chunks, and we know that if we fetch a chunk, it's very much likely that we would be hitting the same chunk for added additional information. And generally, as an optimization, the client would fetch a chunk and its nearby chunks as well. As we will see going forward, it also reduces the size of metadata stored on master, which can become a bottleneck because of the design decision that we take. So hold on this thought, we'll come back to that. So one of the disadvantage of having such a huge fixed size chunk was a couple of them. One was that if a file has a single chunk and all the data is there, let's say 64 MB, and since 64 MB is the smallest unit of data that can be stored, and the whole file is less than a 64 MB, then that chunk will lie in only a single. Then that the whole file data will be in the single chunk, and a lot of clients can go and hit that, and that can become a bottleneck. So that happened with the Google folks when they put some kind of a binary installation or some executable in a single file, and then a lot of clients were hitting it to get and execute it. So it became a huge bottleneck, which they could do it by load balancing and making multiple copies of it, etc., etc. But also, we will now talk about the single master design. So one of the major decision that was taken was to have a single master, to make the design simple. So as as the system got started to be getting used, and I went through one of the retrospective interview of one of the Google tech lead, which we'll talk about in the later time. It was realized that a single master would eventually become a bottleneck, but for shipping this uh, system quickly to the end users, the decision was taken to come up with a single master, and it surely simplified the design to a great level, because the master could be aware of a global state of the system, and it could actually do better decision making. At the same time, it would reduce the number of hops between and complexities between talking, mm, communication between multiple servers. So with a single master, definitely there would be multiple chunk servers. So now we talked about a single chunk, but there will be multiple replicas of that chunk, and there can be multiple such chunks because a file, let's say it's a 64 GB file, so it will definitely be divided into 1,000 chunks, and these 1,000 chunks will be distributed across multiple chunk servers. So let's look at this diagram where we are actually we can see we actually drill down into the master, and we see that what does master store. So master basically keeps a lot of information in its memory. So master maintains which files are there in the Google file system, and it is actually storing this with 64 bytes. So we can say that if there are so many files in the system, and then also it can actually bottleneck and eat up all the memory, because we are also storing one more information, which is the chunk handles. So when the master creates a chunk, it also stores the information about which replicas or which chunk servers this chunk is available at. So if you look at this particular example, you will see that Sudhanshu.txt has two chunks, 1 and 6. So there is one map, one table which stores this information, and the second table stores the information about which chunk server stores the chunk for chunk 1, and which chunk server stores the chunk for chunk 6. So like we can see below that A and C are holding 6, whereas 1 is held by A, B, and D. Similarly, there will be multiple such files. So eventually, it was thought that this master could go and run out of memory, and it could become a single point of failure. But at that time, people employed the Google folks employed various strategies like prefix compression. So what we do in prefix compression is we then don't store the whole path, because this whole path would be repeating to a certain level. So we can just compress it and store that, which which hugely reduces the memory imprint on the master. So master is the single point of failure, as we said. So it required it to have these states persisted. So let's say today I go and change the name of my file from sudhanshu.txt to sudhanshubarthwal.txt, or I want I am creating new chunks, or I increase the version number. We'll talk about the version number concept, but to think to let's say we want to increase the version number, or we want to delete some chunks because these chunks are no more valid. So all this information, if it get lost, then let's say master fails or master reboots, or let's say it dies, it should be able to recreate the state, and for that we needed an operation log to log all these metadata. So what does the meta operation log contain? So it contains all the information that it needs to rebuild the state in case of restart or any failures. So operation log is synchronously replicated to remote master before replying to the client. So what goes into the operation logs? As I said, all the operations or mutation that we do on a master is stored. For example, the file names, the mapping between the file and its chunks, and the chunk, um, and what version numbers these chunks are, and what timestamp these mutation happened on those files, is actually stored in the operation log. However, we don't store the replica locations of the chunk handles. So there is another table which we talked about, right, which stores the chunk handle and the replica information. So this is not stored in the operation log. The reason being, it was actually tried that they should that master should also maintain this. Initially, Google folks designed for that, but it was later realized that, let's say tomorrow a chunk server fails. So let's say a chunk server joins or leaves a cluster, it can cause it will need the master to actually update all these state, and will make the system much more complex and bottleneck it for no reasons. Secondly, the chunk servers actually are the real have the real say on what chunk goes into what chunks they hold. So master relies on that information, and we'll talk about how the master pulls this information from the chunk servers in the next slide. So basically, master actually, whenever the master restarts, it queries all the chunk servers to know which chunk handles they are holding, and then it updates its table to then maintain all the chunk handles and the replica information. Also, it keeps heartbeating all the chunk servers. That is a piece of information that I missed in the last architecture diagram, but basically it actually heartbeats all the chunk servers, uh, and get to know whether the chunk server is alive or not. But along with this, uh, it also uses this heartbeat for piggybacking information, and the chunk server are able to push some push to the master the subset of the chunks that they are holding, and that information, using that information, master is able to update its table and refresh it to make sure that it has the latest information about where which chunk lies where, because it may happen that chunk goes down and then it comes up in another replica, so another chunk server. So the master has this knowledge using the heartbeat, which is very frequent. So it can be slow, because when the server comes up, it has to pull all the chunk server and fetch the latest replica information. Uh, but it is still okay. But we also talked about the operation log. So now we have the information from chunk handle to replica servers, but we don't have the information about the files which are available in this file system, as well as which chunk handles are mapped to that file. So that information is an operation log. So it can be huge. So we have to read it from the operation log. So what we do is we actually periodically checkpoint the state of the master uh, to reduce the time to rebuild that. So checkpoint is nothing but a compact B plus tree which can be directly mapped in memory and used for directly fetching the file to metadata mapping. Now now what happens is that once the checkpoint is done, the older logs are deleted, and if the machine restarts, the the master will load the latest checkpoint and then only replay log after that. So building checkpoint can also take a while, right? So, and we don't want master to actually stop serving request while it does that. So to handle that, what it does is that uh, it it actually whenever a log file is filled, it actually switches to a new log file, and the older log file starts to be checkpointed in a separate thread. Now we know that these operation logs are getting synchronized to another replica, master replica, but which you also call shadow master. We'll talk about that in a bit. But this checkpointed state, when it is checkpointed, is also uh, communicated to the shadow master or the master replica. Now let's talk about the GFS reads. So we understood kind of the architecture. Um, so let's say an application or a GFS client issues a read uh, at a start offset with a start offset and an end offset, and it goes and then this GFS client, since it knows how many chunk, what is the chunk size, it can actually figure out which chunk index has this information, and then it actually sends the offset where this chunk index, inside this chunk index where we need to fetch the data from. So so the information, as we see, right, is going, as we see the information is going here. Um, into GFS masters, and the GFS master will respond back. So let's say it figures out that the chunk index maps to chunk 1, and the replicas that it needs to return are A, C, and E. So it will return that information back to the GFS client, and the GFS client actually caches the file name and the chunk index as the key chunk index, and as well as the server chunk server where it is stored as in a map, and it will have a TTL associated with it, so that until it is expired, the client will keep this information. Now using this information, which is a chunk handle and a byte range, it goes and reaches out to the nearest replica that is available. So a replica chunk server which is in the same rack or in the nearest rack in the data center will be approached to fetch that file, and that's how the read is served. The client typically asks for multiple chunk in the same request, and and it doesn't need to go to the master again and again to fetch this. So now once it might be possible that that somehow this replica is stale and it is not holding the latest information. So what generally happens is that if the client makes a request to this machine, it will get an end of file or something like that, because what happens is that once master detects that the chunk server is stale, it will actually it will mark it as deleted. And now if the client tries to fetch it from here, and ultimately it will either get an end of file exception, or if its TTL is expired, it will go and go to the master and then realize that the new chunk server is available. So it will refresh its cache and then again start fetching from the new location. So essentially, we can say that the time between reading stale data is either the TTL refresh um, or until the replica is marked deleted by the chunk server. So now let's talk a bit about the consistency model that GFS supports, and this is a little bit tricky concept. So we will just introduce this, and then we'll talk about the right flow, and then come back to this again in the end to complete the story. So when we talk about chunk servers, this is wrong. It's not chunk servers, but it is master. So when we talk about masters, the file namespace mutation are atomic. So there is no way that there is anything wrong that can go while we update the mutations. We'll talk about this later. Also, these operations are handled exclusively by master, ensuring atomicity correctness through namespace logging, as I said, and master's operation log, so that the global total order is maintained. So when we talk about consistency, what we talk about is that whenever we read data um, from a source, it should be correct and it should be consistent. So so this paper defines two important terms. One is consistent regions and a defined region. So think about your file or your chunk as and one some of the regions in that chunk. So if all the clients see the same data regardless of which replicas they read from, then it is a consistent region. So what it means is that I have, let's say, 1 2 3 stored in replica 1, and replica 2 also has 1 2 3 stored. So these two are identical replicas, so we say that these are consistent regions. However, it may or may not be defined. So we'll talk about it why we say that. So what is a defined region? So if the client see the complete mutation, so let's say I say that X has to be mutated in replica 1, and Y also is mutating at the same time, but the updates by X and Y are intermingled, and we say jumbled up. Let's say in replica 1 we see X, let's say X is two operations, X and X complement, but in replica Y, and we see X complement Y complement, X double complement Y double complement. So what X complement X double complement are is the first half of the X and second half of the X. Similarly, in replica 2, we see X complement Y complement, X double complement Y double complement. So they are consistent, but they are not defined because a single mutation, this single operation is not atomic. So X operation and Y operations are not atomic. So so this is what we talk in the concurrent mutation. A successful concurrent mutation leave the region consistent but undefined. Like in this case, the both replicas look identical, but I wanted this X to be atomic, but actually this X is not atomic. So I'm not sure that if I issued that, the my 5 rupees should be deducted from my account, and here I said I 5 rupees are added to my account. I'm not sure of what will be the total balance in my account. Similarly, if a failed mutation is there, let's say I issue X and Y and X doesn't even reach all the replicas, then it's a failed mutation. In that case, it will always be inconsistent. So if you talk about it, uh, there are two kind of operation that we defined. One is write and one is record append. So if it is a write, and if it is serial, it will be defined, and it will be defined. And if there's a concurrent success, it will be consistent but undefined. However, in case of record append, we will see that there can be cases like 1 3 2 is written and 1 2 3 are written, but ultimately we will see that a single operation will be atomic. So it can be possible that the two replica doesn't look identical, but they will definitely have the same data. So this is an important concept, and maybe it is not very clear right now, but we will come back to this a little later. So as I said, data is written at a specified file offset in writes, and in record appends, the data is appended atomically at least once. So this is important, at least once, even with concurrent mutation. But the offset that is chosen is by the GFS. So this ensures atomicity and avoid race conditions. GFS ensures that successful mutations result in defined and consistent regions. So as I told, this is applied by applying mutation in the order on the replicas and using chunk versions to detect and handle stale replicas. So we'll talk about this. So what are the major considerations of GFS write? So the key drivers for designing write was, as we said, the one of the assumptions in the beginning was we wanted to optimize on the bandwidth, and make it faster for for the applications to ingest a lot of data, read a lot of data, however in bulk. But however, a single request can take a little bit more time, so we want to utilize the bandwidth in best possible manner. Secondly, we want to maintain the consistency guarantees and ordering guarantees, and have a kind of a model which the applications can work with. It may be a bit relaxed, but it we should be able to work with this. So this is a write control and a data flow. But let's talk about how the data flow was optimized, because we want to optimize on the bandwidth. So actually writing the data on the file was decoupled from actually sending the data to those servers. So there are two steps, right? So one is, uh, we wanted data, the content, to flow uh, through the network efficiently, but uh, we don't want the writes to happen in the same order, because then we cannot maintain the concurrency, consistency, and atomicity. So how the data is pushed is linearly along a carefully picked chain of chunk server in a pipeline manner. So what it means is that the client will push the data to the nearest replica, and the nearest replica is responsible for pushing the data to the next replica which is closest to it. Instead of actually one replica sending the data to parallelly to different replicas. So this was done to minimize the latency by pipelining the data transfer. So basically, as soon as the data is written, accepted by a replica, it doesn't wait, but it's immediately sends it to the next replica in the queue. Once the data is received, it is actually stored in buffer. So this is not visible, but it is like it stores in the buffers that is in the memory, and it actually doesn't apply it or doesn't store it in the final file. So this is a very important point to note, because the client actually issues a write request. So now the data is sent, but the client actually has issued a write request to actually persist this data which has reached in the file. So what is the problem with concurrent mutation? So let's say if we mingled both the data flow as well as storing the data in the same manner. So let's say the data is transferred to one server, chunk server. The one chunk server actually forwards it to the second chunk server, and the second chunk server forwards it to the third chunk server. So it may be possible that two clients are writing at the same time. So one client in one chunk server, x is equal to 1 reaches and x is equal to 2 reaches. In the other, x is equal to 1 reaches and x is equal to 2 reaches. And in the third one, x is equal to 2 reaches first and x is equal to 1 reaches first. And it chooses, the chunk server 3 chooses to apply 2 first and 1 later. So what will happen is that the final state of the x will be inconsistent across the replicas. So we see that in the old in the defined in the table that we saw earlier, the view is not consistent. So we don't have a consistent view, and it is also not defined, because the atomicity is, no, this is not the problem, but consistence, it's not a consistent view. And we also are sure that this is not atomic, so we are losing rights, right? So we same view is not available across the replicas. So that is one problem that we saw. So how did GFS solve this problem? So the GFS solved this problem by actually making sure that only single server or single chunk holder is able to is authorized to decide how the data is applied. So for that, master had to come into the play. So what happens is, there is a concept of chunk lease, where the master actually grants a lease to one of those chunk server. So let's say a client goes to the master for the first time, and the master figures out that chunk one is in. is in A, B, and C. Let's say these are A, B, and C. So, so master then tells that okay, chunk one is available in ABC. Please go and get the data, and for you write the data, and for you A is the primary. So chunk, so master issues a lease to the chunk server one, and this it does using heartbeat messages, and makes it the primary for the chunk server one, for the chunk one. Now the lease duration is only 60 seconds, but these requests can be extended by using heartbeat messages and piggybacking these requests on the heartbeat messages. If the master doesn't hear from the server for more than um, 60 seconds, it is free to choose any other chunk as the primary, and that would not cause any issues because after 60 seconds, the chunk server knows that its lease has expired. Also, master can revoke these leases earlier than the timeout, because there can be times when you want to copy chunk or the file names are changed. So while we do all these operation, we don't want the chunk to be written. So these leases don't work. So how does, so now let's say we made one of the primary as one of the replica chunk replica as the primary. So how does it simplify our concurrent interleaving problem? So here we see that the client asks the master which chunk server hold the current lease for the chunk and the location of other replicas. If no one has a lease, the master grants one to the chosen replica, as we talked later, and it replies with the identity of the primary and the other secondaries. The client will definitely cache this for later mutation and don't need to contact master again and again until the primary becomes unreachable or replies that it no longer holds the lease. The client pushes data to all the replicas to optimize on the data flow, as we saw in the earlier diagrams. Each chunk server stores the data in an internal LRU buffer cache until it is used or aged out. Mm, so we see reiterate again to schedule expensive data flow based on network topology. So right now we are at step three. So in the step four now the client issues are right, and this is done only after it has acknowledged receiving the data. All the replicas have acknowledged receiving the data. The client sends the write. The request identifies the data push. So in the request, we send an identifier to identify that with the primary that this write is for the uh, data ID which is already pushed. Data ID for the data which is already pushed. The primary assigns a serial number to these mutations it receives, and then it actually sends this request to all the secondaries to apply these writes in that particular serial number. So basically, for each data that it gets a write request, it assigns a serial number and sends this write request to all the secondaries. Now, secondaries will actually receive, primary will apply this mutation to its own local state in the serial order. It also forwards it to different secondaries. Secondaries applies these in the serial order, and they reply back to primary that yes, they have completed the operation. The primary then replies to the client if there is any error that is encountered by any of the any error that is encountered by any of the replicas is reported to the client, and the client has to retry. So now let's look at the challenge with the writes. So let's say we have three chunks in two chunks, chunk one and chunk two. Sorry, this is chunk two. Let me pick up the black and and they are available in chunk server one and chunk server three, and there is also chunk server two. So this is wrong. So we'll look why it is wrong. So we'll see what is the final values of mutation. So we have two atomic operations, W1 and W2. atomic operation 1, atomic operation 2. And we have two values that we are mutating, x and y. And let's say these x and y lies on the chunk boundary. So at the end of the chunk, we have x, which lies in chunk 1, and there is another value y, which is in the chunk 2. So let's say w1 operation comes, and w2 operations comes, and they are transferred to each of these servers according to the data flow. So from client B, server 3, the operation comes here, and it comes here, and like similarly, one of the operation comes here, another operation comes here. So let's say W2 is coming from here, and W1 is coming from here, and ultimately since primary for chunk 1 is in server 1, and primary for chunk 2 is in server 2. So the authority to mutate the value of x lies with server 1. However, the authority to mutate the value for chunk 2, which has a value y, lies with server 3. Why this is? Because primary can select any of the replica as the primary. Master can select any of the replica as primary and can provide it lease. So now if server 1 primary chunk 1 decides that the order of operation should be W1 to W2, so the x, which it has a say over because chunk 1 is primary, so it will have the say, and the final value will lie according to W1 W2, and W2 x is equal to Raj, so the final value of x will be Raj. However, for y, the authority for deciding the order will be with server 3. So the order that will be followed will be W2 W1, and in W1 the value of y is engineer, which lies in the chunk 2. Um, so the final value after the mutation will be engineer, since server 1 doesn't have any authority over value y, because it lies in chunk 2 and it is not the primary, so it will get overridden, and the final value that will be present after mutation will be this. Sorry, in my slides I mistakenly picked student artist, but it would be Raj and engineer. So now we see that the region may end up containing fragments from different clients, although the replicas will be identical because the individual operations are completed successfully in the same order according to the chosen replicas. So we see that the region is inconsistent and undefined. So with random writes, we will always have this problem. Solve this problem, Google file Google team decided that they don't want to solve this problem, but actually, since they want to optimize for atomic record appends, they came up with a appends. They came up with an operation called atomic record appends, and in a record append, the client just specifies the data, and GFS will choose where to apply this data, choose the offset where to apply this data, and it will apply at least once. So this is a very important term. So it all follows the same control flow described above, but with a small change. So primary checks to see if appending this record to the chunk would cause the chunk to exceed the maximum size limit, which is 64 MB. If it sees that this chunk cannot come into this particular single chunk, it would not write to multiple chunks. It will not break the operation into multiple chunks, but it will actually pad the remaining chunk with whatever size is remaining, and which will essentially be not more than 1/4, because the maximum size of um, the data that can go in a single operation is 1/4 of the chunk. It also tells the secondary to do the same and replies to the client indicating that the operation should be retried on the next chunk. Now, this helps us solve the problem that we see in the previous slide of interleaving between concurrent operations. But it may happen that the record append fails at any replica, and now the client retries the operation. As a result, replicas of the chunk may contain different data, possibly including duplicates. So we'll see this scenario where let's say we write to a single we write to multiple replicas. Let's say there are replica 1, replica 2, replica 3, and the data reach two replicas, but it couldn't reach this, so the operation will fail. And the client will retry again with the same operation, and now there will be a padding here, and there will be duplicates in two replicas, where there will be no duplicate but a padding in the third replica. Now we see that due to this, the data is defined because we have solved the problem of concurrent updates on the boundary, and now no longer we can have interleaving due to two reasons. One, that we serialized using the least primary, and secondly, not writing on the boundaries, and thirdly, due to the appends, we are able to solve this problem. But the two replicas can be divergent, but we are sure that there is one single write which is at the same offset on all the replicas. There can be various regions which are undefined, but these regions, this is the consistency guarantee that we give, and the clients are supposed to deal with this. We'll see a little bit more in the next slide. So as we said, we cannot guarantee that single writes um, uh, can be the single writes can be consistent and defined, but with record appends, we can definitely say that it can be defined, but there can be interleaved areas which are inconsistent. So, so let's look at this. So we actually already covered this, but to reiterate the aspect, as I said, right, if some client wants to write X and it succeeds on two replica, fails on one, but then it retries and it succeeds in all the replicas, we see duplicates somewhere and we see padding somewhere. Hmm. But there is one more case that may happen, and that is that which generally which can happen in GFS. If X is tried and X goes into two replicas and not in the other one, and then Y is written on the three replicas, and then X is again tried, but it still reaches only two replicas and not the third one. So this state is also possible, where one of the replicas never have that information. So 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 this is an implication for the client, and the client need to handle this kind of inconsistency, where we see that data are defined, but there can be interleaving regions which are inconsistent. Like this is an inconsistent region, this is an inconsistent region, and there are various methods that client need to employ to solve this. We know that the fourth assumption that we had was that co-designing with Google applications, right? So what we meant by that is that there will be various decisions that will be taken in GFS for which clients have to be prepared and include while developing their applications. So one was that they had to handle the consistency issue with themselves. Also, the rights were not optimized and could be inconsistent as well. So, appends was the way to go, and atomic record append was the only way to ensure that they had defined regions with intervening regions which were inconsistent. For handling this, the applications are expected to periodically checkpoint their progress, including application level checksums, allowing readers to verify and process only the defined regions and ignoring all the inconsistent regions. Checkpointing allowed writers to restart incrementally and keep readers from processing regions that were successfully written, but they were incomplete because from the application perspective. And that helped in making sure that they don't read any corrupt data. So there was an interview from one of the Google file system, and that is published in the ACM discussions. So he was asked what exactly was the loose consistency. So he says in his words that what happens is that primary will try, it will pick an offset, it will do writes, but then one of them won't actually get written. Then the primary might change, at which point it can pick a different offset. Record append does not offer any replay protection either. You can end up getting the data multiple times in the file. There are even situations where you could get the data in different order. It might appear multiple times in one chunk replica, but not necessarily in all of them. If you're reading the file, you could discover the data in different ways at different time. At record level, you could discover the record in different orders depending on which chunks you happen to be reading. So the point is exactly what we covered in the last slide, where it may be possible that one of the client replica never gets the write. So eventually, for a client, that write is failed, but it will be there in the GFS system, and the client has to make sure they're able to differentiate those. At the same time, they should be able to handle padding, duplicates using checksums and unique identifiers. So GFS provide library support to handle such inconsistent delivery of records so that the end user gets the data correctly with occasional issues. Now let's talk about the last operation which Google File System supports, and it's a very underused operation, which is a snapshot operation. So what happens there is that it allows for creation of a copy of a file almost instantaneously. So it is achieved using copy on write techniques. So basically, whenever a snapshot request is received, the master first revokes any outstanding leases on the chunk so that nothing else could be written while the snapshot is being taken. It logs the operation and duplicates the metadata for source files. At this point, it doesn't actually create a new copy of the data. But the first time a client writes to this chunk after the snapshot, master creates a new chunk of the same chunk server to ensure local data copying. So basically, it will create another replica in the same server where the current chunk is there before actually it writes the new data. This process enables efficient branching and checkpointing of large data sets. So we come back again to the master operation. We talked in initially about namespace map management and locking, and what how it does is that it uses a lookup table. Internally, it is just a lookup table of file name and which are prefix compressed, and each node each node in the namespace tree is has a read write log. So let's say we want to create Sudhanshu.txt, or we are writing to Sudhanshu.txt. So the home folder will have read access, home users will have a read access, but home user Sudhanshu.txt will have a read access. Now let's say we want to copy home users to save users. So in this case, home and home users will have a write lock, and save users will have a write lock. So now the two operations that are fighting are snapshot and create. So we'll have to serialize the operations in home in creation of Sudhanshu.txt and creating a snapshot. So one of them will be serialized. So we make sure. So another important aspect to this is, let's say we are writing multiple files in the same folder, home users. So home and users will have a read log, and that will help us create multiple files in this directory hierarchy at the same time, and thus reduce bottleneck and not cause concurrency issues. Replica placement, one of the very important aspects of master's operation, is how it actually places these chunk replicas, and that is very important because one of the primary reason for making a single master is that it has a complete view of the whole health state and doesn't have to depend on anyone else for knowing where exactly what is. So replica placement is all the logic for that is placed in master, and it will do that based on various criteria. One of them being, if there is a below average disk space utilization, it will actually put those replicas new replicas on those servers. Secondly, it will see where it is creating the recent chunk servers, because those are the chunk servers where the most writes are happening. So if it wants to load balance the writes, it needs to make sure that it doesn't put all the replicas that are getting created in the new chunk server, because we know that once the chunks are filled, and we know that GFS only follows append, so there will not be a lot of write requests on the single chunk server. So if there are many read replicas, like chunk servers, chunks which were created not very recently, then we are sure that it will get only the read workload and not a lot of write workload. So replicas are also spread across racks to maintain the upgrade domains and the fault domains, so that failures doesn't cause everything to go down. The goal of doing this is to maximize the data reliability and availability and maximize the network bandwidth, because if we put these replicas across rack, we are also increasing the aggregated bandwidth utilization. This is required apart from making sure that there is no that that things are still available even if the whole rack goes down. So master also has to do a lot of creation, re-replication, rebalancing. So let's say a chunk goes down, so master needs to spawn a new chunk in a new replica, so that is something that is done by the master itself. So how does how does it decides which request to do first? So basically master will re-replicate chunks as soon as number of replicas fall below a user specified goal. So now it prioritizes those replicas which actually all those chunks which who are far behind the defined goal, and also it will prioritize replicas which are much more recent and are much getting much more traffic. So we may also choose to boost the priority of the chunks that is blocking the client progress, and that will help us in actually making sure that we are actually re-replicating the master is re-replicating only the chunks which are much more in demand. So the goals for this is pretty similar to um, the placement criteria, like utilizing the disk specialization and limiting the active clones, and limiting the spread of and spreading replicas across traffic. One of the more important uh, operation that master does is garbage collection, and it does it lazily. So garbage collection, as we know, if you have used certain languages, you would know that it's pretty hard to detect the garbage, right? The free pointers or the pointers that are dangling and should be removed. But in case of uh, even in case of distributed system, it is hard. But in case of GFS, it's pretty easy because we handled it using a single master. So how does it does that do that? How simply it does that? We'll see the beauty of it here. So master logs the deletion, just like other changes. So it gets to know that this chunk um, has to be deleted. Either it gets the request from the client, or um, uh, and it marks those file handles or chunks as deleted. The file is renamed to hidden name, and a deletion timestamp is associated to that. Now, master does a regular scans, and it removes any such hidden files if it exists more than 3 days. Now, once the file is removed, a corresponding metadata for chunk is deleted as well. In the similar regular scan, it also checks whether there is any orphan chunk, and there is no chunk handle to those chunk in the metadata table for those chunk handles. So what it means is that there is a chunk handle, but there is no file to chunk handle mapping. So it will remove those metadata from the from its another table, which is chunk to replica table. In regular heartbeat message, chunk server reports the master subset of the chunk that it holds, and the master will reply back with identity of all the chunks which doesn't have a parent anymore. The chunk server now, using the heartbeat message, know which chunks are now without any handle and are free to be deleted or garbage collected. So the advantage of having a lazy garbage collection versus eager deletion is that we defend against mistakes and irreversible deletions. For example, I delete a file, but later on realize that I want to recover it, so I have still 3 days to recover that. Simple and reliable as deletion message can be lost if it has to be synchronous. But here we are just marking what we want to delete, and then the master takes care of it lazily. Storage reclamation is also merged in background because there are multiple background jobs that are running, and in batches it can be done, so it amortizes the cost rather than pointed request for deletions. The disadvantage is that if there is a resource crunch on various node servers, it can make lazy garbage collection can make it hard to reclaim such back storage. So to do that, if multiple deletes are sent, then it expedites it faster. So the master maintains chunk version to identify and manage stale replicas. So whenever a new lease is associated to a primary and a primary is decided, the master bumps up the chunk version and stores that in its own operation log. Now, if um, the master goes down or it comes up and it tries to poll the replicas, and it finds that the chunk servers, one of the chunk server has a lower version number than it has, then it actually marks that as a stale replica and reports it. So the master then removes the stale replica during garbage collection and ensures um, client access up to date data. It may be possible that while the master is down and it comes up, it realizes that the chunk version number on one of the server is higher than it. So I don't know exactly why this happens, but if it finds that the chunk server has a higher version number, then there might have been some other master. Maybe this was a shadow master which was promoted as a master, and it doesn't have the latest version number, so it accepts the version number that the chunk server gives it, and that is what it replicates, propagates to other chunk servers and make them up to date, so that the client only gets the up to date data. Now let's talk a bit about the fault tolerance. So to handle fault tolerance, multiple replicas of each chunks are created. Replicas are spread across different racks, and the master state is also replicated for reliability using the checkpoints and operation logs. And this is done on multiple machines as well. So the master is also replicated. So I know that we know that there is a single master, but there is a shadow master. We'll talk about it in the next slide. Fast recovery, quick restart of master and chunk server. How do we achieve that? Is through through operation logs, checkpointing, so that the operation log doesn't grow to a huge size, and making sure that it recovers. So one more thing is, if the master itself goes down, the monitoring infrastructure outside GFS makes sure that it spawns up a new master, mm, spawns up a new master, or it um, uh, where new master where it actually has the replication log, and that is the shadow master. For data integrity, the checksum is done to make sure that while we read and write data, we actually are reading the right data, and we verify the inactive chunks as well. If a machine or disk fails, we said that monitoring infrastructure outside GFS starts a new master elsewhere. And where does it do that is a shadow master. So we know that So generally, a shadow master is not a slave, but it is actually also serving requests. So apart from the oplog apart from the data mutations on the master, all the other replicas chunk server can also report their information to this shadow master as well, and it can actually load balance the load with the clients. And there can be two masters who can be serving the request. However, the shadow master will might have a little bit of lag because it is actually reading its state from the operation log of the master, the main master. And once this main master dies, the shadow master may become the real master. Now let's talk about the data integrity. So we said that when we read or write the data, we want to make sure that we don't read the wrong data, and the replica doesn't have the server doesn't have a corrupted chunk. So to do that, we have checksum. So every 64 MB block is divided into 64 KB blocks, and each of these KB blocks has a 32-bit checksum, and it stores all the checksum in a memory. However, this checksum is also persisted in a log which is separate from the user data. If a block does not match the recorded checksum, mm, the chunk server returns an error to the requester and reports the mismatch to the master. And then the master marks this replica as stale and tries to copy the chunk from some other replica. So in case of record appends, the chunks checksum creation is pretty simple. So as we append, we incrementally update the checksum. So let's say there is a 632 KB block, 64 KB block of chunk. One of the chunk has one 64 KB block and it is partially written. So if we add more data to that block, the checksum will be incrementally updated and it will not impact the older checksum for the rest, the bytes that were written before that. Now, how this is helpful in case of appends is that we don't actually overwrite the data. So even if the older checksum data was corrupt, it will be detected if we if um, someone reads back later on in the time, and we are sure to make sure that we always read verified and correct data. However, in case of overrides, um, when we override these blocks, the whole checksum is recalculated for the full block. So let's say half of the, so let's talk in the next slide. So let's say there are three blocks in a, so we are talking not in, these are not chunks, but these are blocks. So there is a block one, block two, and block three, and let's say half of block one and block three are written and full block two is written. Then for block one, if we write even partially on into that block, we will have to recalculate the checksum for the whole block. And now what happens is that, let's say before we could write, there was this first half, the first half of the data. So this one, the first half of the data was actually corrupt. So now we recalculate the checksum for the whole block and we update the older checksum. And now we don't know the older data which was here, which we used for creating the checksum for this block, is it stale, is it corrupted or not? Because next time we read, this checksum and this checksum will match. However, in case of append, it was not the case because this checksum was never overwritten, and whenever we were appending, we were only calculating checksum incrementally for this area. So this is a pretty nuance that took me a little while to get hang of, but I think this is the way the team is doing this. Well, we come to the conclusion of the global file system. It has been a pretty intense paper and a long paper, but I think one of the greatest uh, highlights of this system was that it has been widely used for research and production across Google's, and it has proved a lot of hypotheses that a lot of folks had before implementing such a large scale distributed system. So this is one of the first systems that actually was a very successful system and still is great. However, in retrospect, I'm referring to the interview by the Google engineer later on, and in retrospect, there were few decisions that the team realized were not really good. The awkwardness of supporting an ever-growing fleet of user-facing latency-sensitive application on top of a system initially designed for batch system throughput is something that is obvious to all. As GFS grew, Google teams started adopting it, and there were various kind of workloads. And it was not only the batch workload, but there were workloads which had smaller file size. There were workloads which needed a lot more metadata in the memory, and this all led to various problems. Like single master eventually became a bottleneck because there was so much memory you could add to a single machine, and as the number of files grew and as the number of uh, chunks grew, memory ran out. So now they came up with a change in the design where they actually came up with cells, which are called master cells. And now it was no more a single master, but it was there were multiple master cells, and the client or the application was supposed to load balance or shard their data across these master cells and its associated chunk servers. Chunk size proved to be a top big problem because it was realized that most of the Google, as the Google applications grew, they were like Gmail and such things, that they wanted to store data which was not that large as 64 MB. And I think Bigtable and such system which were built on top of Google File System tried to solve this problem or mask the problem which Google File System had. So in case of record append, we touched upon the problem where consistency was very loose, in the sense that it was very hard. It might be possible that it was a lot of exercise for the client and the SDKs to make sure that they are able to handle this relaxed consistency where data is duplicated and not very in order. So the Google engineer actually says that it turned out to be a lot more painful than anyone expected. But all in all, this paper actually gave me a great insight into what were the challenges and how they were being solved with keeping the design very simple, and proved to be a very good system in the end, which could solve a lot of problems mm, for the Google team. Thank you.